Hello guys, I am back with another YouTube marathon of cryptography. So I am going to cover the topics in cryptography, how the algorithm works, how do they work in real life, and about cryptography, what are the algorithms and mathematics, what are the key encryptions are used in cryptography. So let's get deep dive into it, and I'm going to make sure that I make some notes, making sure that I remember this time. So let's start. My name is Pinaki Misha. I'm back on my YouTube channel. Go. So first we will start with our cryptography one. No, this material is not intended to replace live lecture for students. Okay, so I'm going to tell you that it belongs to Politecnico di Torino. So whatever I study here belongs to Politecnico di Torino, and whatever I am going to teach and learn here is also belongs to Politecnico di Torino because the content I am getting from is Politecnico di Torino. I am a student there in a master's first year. So let's get dive into it. So what is Gen? Enc and Dec. The gen is key generation, generating a key. Enc stands for encryption. Dec stands for decryption. Introduction to cryptography. The art of science keeping a message secure is cryptography, and it is practiced by cryptographers, cryptanalysts, practitioners of cryptanalysis. The art of science of breaking ciphertext that is seeing through the disguise, the branch of mathematics and encompassing both cryptography and cryptanalyst is cryptology, and its practitioners are cryptologists. Modern cryptologists are generally trained in theoretical mathematics. They have to be. So, what is cryptography? Cryptography is the art of science keeping messages secure. What is cryptanalysis? The art of science of breaking the ciphertext. So, let's get into it. Security through obfuscation. If I take a letter, lock it safe, hide the safe somewhere in New York, and then tell you to read the letter, that's not security, that's obscurity. On the other hand, if I take a letter and lock it in the safe and then give you the safe along with the design specification of the safe and 100 identical safes with their combination so that you can and then you and the world best safe crackers can study the locking mechanism and you still can't open the safe and read the letter, that's security. So important ideas in cryptography were developed before the computer era, but along this course, we are interested in the computer related problems, communication between computers separated by space, communication between computers separated by time, example to cipher a hard disk. We are going to use Python. Here is the link for Python basics, medium free code camp, Python from zero to hero. Actually, at the end of this course, it should be possible to read any and try to understand the documents and the type are here in NIST SP. Downloading hacking cipher secret ciphers with Python and look to the chapter 1. It's not just an encryption, authentication, integrity, and non-repudiation. Authentication. It should be possible for the receiver of a message to ascertain its origin, and intruder should not be able to masquerade as someone else. Integrity. It should be possible for the receiver of the message to verify that it has not been modified in transit, and intruder should not be able to substitute a false message for a legitimate one. So, a person who is not able to play with the file and the file should not get changed, it should be legitimate one, so that is called integrity. Non-repudiation. A sender should not be able to falsify, deny later that he sent the message. So non-repetition, a sender should not be able to falsely deny that later he sent the message. So a person who sent the message on WhatsApp, Instagram, whoever it is, the non-repetition is he is not able to delete the message and say that I didn't send it earlier. That's it. The destination is secure. That there were no non-differentiate during transmission. Here we are attached strongly the power of cellular, so we need that to the host our computers. Without them, these cellulars would be impossible. For example, with Defi helmet, it is literally impossible to do by hand, even if there might be a simple exchange. Cryptography basics. Symmetric, asymmetric cryptography, symmetric key generation. We have this measures of security. The way key size is the lambda, usually represented as a user initial 1 is to power 128 equals to 111, and this is 128. And this type of crypto is classic one. We do have the same key for the encryption and decryption process. So this lambda is like 1 is to power 128. This generate a key and then it converts into the key itself. This is symmetric key generation. This is keygen asymmetric, same parameter, but we have two keys here, secret key and private secret key and public key. Here, instead of the genre gives two keys. Okay, here are some important jargon. P equals to plain text, clear text message, sometimes also indicated as M. K equals to key, PK equals to public key, SK equals to secret key. Gen equals to key generation algorithm, enc is equals to encryption cipher algorithm, encryption ISO 74982, and cipher C equals to ciphertext cryptogram, dash equals to decipher algorithm, decryption ISO, and it used the decipher. And there is lambda, security parameter or level measure in bits. Example here, standard values are lambda equals to 128, 192, 256 and 512. As we all know, according to the security, 128 and 192, 256, these are the IP addresses. As you can know, these are divided in real life example. So cryptanalyst, enemy, eavesdropper. So someone who tries to hack into the system. Attack and break. Spaces, example key spaces is like this, special type of K, or message space is M, special type of M. Force froze brutal attack, to check all K equals to special key space key, or all M equals to special M, which is message space, etc. To use crypto, all parties must agree on all the elements defining the crypto system, that is the domain parameters of the scheme, all the elements that must be known both the parties of the common communication. I say. So I think this is easy to understand. Cryptographical primitives. Cryptographical primitives. A cryptographical primitive is a fundamental building block used in cryptographic protocols and algorithms. These primitives provide basic functionalities and are combined to implement more complex cryptographic operations. Encipher, decipher, symmetric. So we have this plan, key, plain text. I think this is plain text. We have the key, we have the encryption, and then we have the cipher. Then here we have the cipher, we have the key, we have the decryption, and then we have the plain text. So it's the same thing, that cipher is the same thing. We use only cipher key for the encryption. For the most symmetric primitive, block cipher. Data encrypt in fixed size blocks. Data encryption standard AES, advanced encryption standard, keygen NIST SP 800 133, blowfish, two fish, serpent, not specified, and stream ciphers are RC4, SALSA 20, CHA 20, encrypt data 1 bit or byte at a time. Message authentication codes MAX provides authentication and integrity. HMAC hash-based message authentication system. CMAC cipher-based message authentication system. GMAC Galilius message authentication code. So we have this type of. I think we should have the real life example for these things. I hope I just need till block cipher. Okay, it's coming all. Give me a real life example for this one. Block ciphers in real life encryption AES used in HTTPS, Wi-Fi security WPA2 and disk encryption tools like BitLockers and Firewall. 3DS, triple DES, previously used in banking system and legacy application. Example: EVM chips, cards, Blowfish to fish. Used in tools like OpenSSH and some VPNs. Serpent, considered for AES competition, used in some niche cryptographic libraries. Stream ciphers in real life. Stream cipher encrypt data 1 bit or byte at a time. Ideal 1 bit ideal for real-time application. RC4 formerly used in SSL, TLS, and WEP, now deprecated due to vulnerabilities. Okay. Salsa 20, Chacha 20, used in modern secure messaging like WhatsApp, Signal, also in TLS. Example: Chacha 20, Poly 1305 for mobile performance. So, message authentication codes MAX. MAX ensure that the data hasn't been tampered and confirm the sender authenticity. HMAC used API authentication, example AWS, TLS, and secure file transfer. CMAC used in embedded systems, smart cards, for example, secure firmware updates. GMAC used in AES GCM mode for authenticated encryption in TLS and IPsec. Okay, these primitives are often combined in protocols. For example, TLS used in HTTPS uses AES or SHA256 for encryption, uses HMAC or GMAC for integrity. HMAC HMAC is hashed based message authentication. GMAC is Galilius message authentication. Uses RSA or ECDHE or key exchange. Now this is not here, I think. Signal protocol used in WhatsApp. Signal. Okay, uses AES or SHA256. Uses HMAC for double ratchet or X3DH for key management. Okay. So what are the key derivation functions? Derived one or more secret from the secret value PBKDF2, password based key derivation function 2, bcrypt, scrypt, argon 2, random number generation, generate random numbers for cryptographic use, cryptographically secure PRNGs, CSPRNGs, and we have this hash function which is SHA256 secure hash algorithm. SHA3 we have MD5, this is also a hash function. Consider weak, then we have RIPEMD which is 160. So let's get these in the real life example. Password storage PBKDF. Okay, password based, this is used in WTA2 Wi-Fi. Bcrypt adds salt and computationally expensive to resist brute force attack. Bcrypt is strong. Scrypt, memory hard, designed to resist hardware attacks. Example ASICs. Okay. Argon 2, winner of the password hashing competition. PHC. Considered the most secure and modern KDF. Random number generators. Purpose. Random numbers are essentially in cryptography for generating keys, nuances, and initialization vectors. CSPRNGs, cryptographically secure pseudo random number generators. These are the designed to be unpredictable and secure against reverse engineering. Okay, reverse in this is our more secure. Example include there you are you random or Unix system, Windows cryptogen random, NIST DRBGs, which is deterministic random bit generators. We have the hash functions. Purpose hash functions take input data and produce a fixed size output hash. They are used for data integrity checks, digital signature, password hashing, blockchain, and cryptocurrencies. Example, SHA256, part of SHA2 family widely used in Bitcoin, TLS, and file integrity. SHA3 based on Cipher algorithm, a new standard with a different internal structure. MD5, once popular, now considered broken due to collision of vulnerabilities. RIP EMD 160, used in Bitcoin address, offers 160-bit hash output. Okay, so these primitives are foundational tools in cryptographic system. For example, when you are log into a secure website, your password would be PBKIDF2, which is a password based derived key derived function. CSVRNG generate a session key. The session uses SHA256 to verify message and integrity. C. So now we have this Encipher and Decipher asymmetric key. Here we have public key, we have secret key, and we use this as plain text. Then public key comes while doing the encryption. Both are doing encryption. Then we have this ciphertext. Then ciphertext, if anyone wants to decrypt it, they need to use secret key and decryption and use the ciphertext that they have, and that algorithm gives you plain text. More important symmetric primitives, public key cryptography algorithms that are used a pair of keys, RSA, Shutter-Edelman, ECC, elliptic curve cryptography, DSA, digital signature algorithm, Gamal encryption. We have this digital signatures verify the authenticity and integrity of a message. RSA signatures, ECDSA, elliptic curve digital signature algorithm. EDDSA, Edwards curve digital signature algorithm. Key exchange protocols allow secure key agreement between parties. Diffie-Hellman key exchange, ECDH, elliptic curve Diffie-Hellman. Then we have identify based cryptography uses any public key. So okay, then we will go to workshop. Let's see what are the mm, give me the real life example that is using the above. So surrounding from the crypto one introduction, we have email encryption, PGP, and digital certificate X509, epileptic curve cryptography used in mobile apps like Signal, cryptocurrencies, example Bitcoin, Ethereum, TLS for faster, lighter encryption, DSA, digital signature algorithm used the digital signature for government documents and secure software updates. Algamal encryption used in some PGP implementation and academic cryptographic systems. Digital signatures, RSS signatures used in software signing, example Windows Update, SSL, TLS certificates. ECDSA used in Bitcoin, Ethereum for signing transactions. EDDSA used in modern secure messaging apps like Signal on WhatsApp for fast secure signatures. Diffie-Hellman used in VPN, TLS order version. ECDH elliptic curve Diffie-Hellman used in TLS 1.3 signal protocol and secure messaging app for efficient key exchange. Identity based encryption (IBE) used in secure email mesh systems. Example: voltage and secure mail, military communication, and enterprise key management. This is really juicy stuff. We have this Kirchhoff's principle. Kirchhoff's principle. The difficulty to break the system should be in the key. So security has to be built only the secrecy of the key. Kirchhoff principle is the enemy knows the system, Shannon maxim. That this means that the security should depend on the secrecy of the key. So key should be secret. Computationally infeasible and security level. Memory of CPU needs are too high. We will task computationally infeasible of its cost as measured by either the amount of memory used of the or the runtime is finite but impossibly large. So memory or CPU needs are too high. Okay, computationally. Okay, so requirement runtime. Okay, runtime is finite but impossibly large. So we need a big, massive computation power if we want to do this. So we have this to get a clue of a meaning computational infeasible. Imagine you are looking for a key K of m bits. K, okay, 0 and 1 m. What does this symbol mean? Element of. Okay, so this is an element of. K is an element of 0, 1 and m bits, which is 0 and 1. 0, 1 forms brute force 30 bits. From timeout, import default timer as timer loop with 2 star star m rounds. M equals to 30, start equals to timer, j equals to 0 while j is less than 2 star star m. Try with key k underscore j. Print j plus equals to 1 and timer. Print the total time employed to check all the keys. Print m and start 60 minutes. So it will take 1 hour. Time in minutes. The m parameter here is lambda. So the exponent of z measure the security of the key. How long it takes m equals to 64 bits? Take a look at part 10, page 12. Table 1.2, Schneider 15, page 18, table 1.1. Note, in Python here are two of them, 0 and B, format 22, int 0, 1, 0, 0, 1, 2. These are the some Python related hexacode, I think. So they are having this format data structure.html and encryption algorithm. Okay, let's solve this with the help of Copilot. The exercise built on previous section 1.2.6 where the concept of brute force act is introduced. The idea is estimate how long it take to all. Okay, this asks you estimate the time brute force is space size of twist power 64 assuming try to each. Okay, Python examples. Yeah, this converts the integer 22 bits to its binary string representation. Okay. Okay, so this is the binary bit representation. Hmm. Converts the binary string to its decimal value, which is 9. Oh. This section encourages you to understand the computational feasibility of brute forcing large key spaces. Use Python to simulate or analyze such scenarios. Refer cryptographic literature to ground your estimates in real world performance data. 64-bit, an encryption algorithm has a security level of n bits. If the best known attack requires O is to power 2n steps, this allows to compare algorithms and is useful when we combine several primitives in a hybrid crypto system. To understand any weakness, the security level is related to a security parameter lambda or k, which is usually written in unary 1n. In most cryptographic functions, the key length is important security parameter. Sometimes the num of bits is equal to the security level. Okay, let's learn this in real life example. N bit security mean algorithm security based on 2n operation. This way measure how hard to break an algorithm using brute force or the techniques. Okay, approx security level 128 bit, and okay, so it's defined by bits, security of bits, RSA, AES, SHA, ECC. Used in mobile applications, cryptocurrencies, used in TLS certifications, used in HTTP VPN encryption. Why it matters? Comparing algorithms, you can compare symmetric and asymmetric algorithms by their effective security level. For example, RSA need much longer keys than AES to achieve them securely. Hybrid crypto systems in practice system often combine multiple primitives. Example RSA, EES, HMAC. The overall system is only as strong as its weakest link. So knowing each component security level helps assess total system's length. Security parameters M or E, often written as 1 is to power n, is unary. Parameter defines the desired security level. For example, m equals to 128 means the system should resist any attack requiring fewer than 128, 2 is to power 128 steps. Real world analogy, imagine safe combining with a 3-digit lock. 00099 has 1000 combinations of 10-bit security. A 6-digit lock has 1 million combination with 20-bit security, and 128-bit keys has 2 is to power 128 combination, particularly unbreakable with current technology. Okay. Would you like a Python level simulator brute force time for this security levels? The copilot is telling me to break this down. 3 toy examples of symmetric ciphers. Alice have message of constructed of using plain text of 5 bits speed for this. P is equal to 11100, and wants to send them to Bob Oscar is a eavesdrop. Vernam cipher. The motivation of using 5-bit in this example is Baud code for a telegraphy invented by Emile Baudot in 1970s. Baudot code is a predecessor of IT2 code, which was until the advent of ASCII. Baudot developed his first multiplex telegraph in 1872 and patented in 1874. In 1876, he changed from a 6-bit code to a 5-bit code as suggested by Carl Friedrich Gauss and Wilhelm Weber. In 1834, the code itself was not patented, only the machine, because French patent law does not allow concept to be patented. Okay. So the Vernam cipher or Zor cipher, i.e. Zor. Alice Bob meet somewhere and agree on using k equals to 0 1 0 1 0 as their secret key. Alice is having their cipher encryption key plain text equals to plain text XOR key and then cipher, and then it goes to Bob, and I think okay, Bob uses the plain text, then decryption key and ciphertext equals to, which is ciphertext XOR key. So we are using here. Notice that the key is the binary representation of the number 10 equals to 0 1 0 1 0 is to power 2. Any plain text p01 can be regarded as the number 0 p2 is to power 5, which is 32. By using the code, we have this 0 1 Alice cipher message M sent to Bob following the ciphertext, and this is the ciphertext. Let's learn this in more layman terms. I think that would be more beneficial for us. With a real life example so that I can understand and solve it. Okay, if we can solve this one. Vernam cipher or Zor cipher, how it works. So, whoever might be listening. So Alice and Bob agree to create a secret key, use a simple encryption with a Vernam cipher known as Zor cipher. How it works: plain text, a written 5-bit key. Okay, they have this key cipher, a secret 5-bit binary number. A secret 5-bit binary number. Both Alice and Bob know, which is 0 1 0 1 0. Ciphertext: the encrypted message Alice sends to Bob. Encryption and decryption: to encrypt C equals to P XOR K, and to decrypt P equals to C XOR K. This works because XORing twice the same key gives you the back the original message. Real life analogy: Alice writes message using secret code book, the key. She scrambles each letter using a simple XOR rule. Bob has the same code book and can unscramble it. Oscar sees the scrambled message but can decode it without the code book. Example in action: let's say Alice wants to send the letter T, which is encoded in 11100 from 5-bit out style code. The secret key is 0 1 0 1 0 1, which is a binary for 10. Step 1: encrypt P equals to this, K equals to this. This is plain text, this is key. We have this P or K, which is okay. Now we can do this: 0 0 0 0 1 0 0 1 0 and 1 0 1. So this is the encryption, and then we have the decryption here, which is the ciphertext first, then Bob decrypts it. We have the key would be same, just the P and ciphertext both changes, and then 0 1 1 0 1 1 1 0 1 1 1 0 and 0 0 0, which is T. So why 5 bits? The note mentions borrowed code, a 5-bit telegraphic code from 1970s. It was used before ASCII and could represent a letters A to Z. And a few symbols. That why a toy cipher uses 5-bit message. It's simple and historically meaningful. Real world use. Vernam cipher is based on the one-time pad, which is perfectly secure if the key is truly random, as long as the message and never used. Used in highly security communication example like military and diplomatic channels. This is secrecy. So we have the another exercise. After some days, Alice and Mommy again decided to change the key to a new one, K01 is to power 5. Then Alice, by using the new key, encrypt M, which is message, I think, and send the following cipher text to Bob using this. Can you find the new key? Okay. So let's see where is the new key. Caesar cipher or Zor cipher modular addition. Here instead of modular we use the XOR operation. I mean instead of XOR we use the other thing, Caesar cipher. This is called Caesar. This is called XOR. An operation which means the sum of with carry a bit up to 5 bits, for example 11011, where we have this here. I think we have so many here. So 1 1, and then we have 10 and 101, which is equal to 10,000. So let's see how it is 10,000. Caesar cipher operation is easily base 10 representation arithmetic modulo 2 is to power 5 equals to 32. 27 modulo 27 cipher Caesar. 27 Caesar 21 equals to 48 equals to 16 more 32 LSC encrypt KP equals to P Caesar K, and then we have Bob. Okay, Bob have the plain text decryption key cipher text and then cipher, and then he has Caesar, which is minus K, which is the key negative key. Here an example with the key equals to K equals to key equals to 3. Tomorrow I cannot attend Alice. P is this, C is this, and okay. Let's learn this thing in real life, easy manner, layman terms. Okay, cipher. Mm-hmm. How did they solve, and how the modular works, modular addition works in this case in layman and easy terms with real life example. What is the Caesar cipher? Caesar cipher is one of the oldest and simplest encryption techniques. It works by shifting letters in alphabet by fixed number of positions. In this example, we working with 5-bit binary numbers which represent characters using a custom alphabet of 32 symbols A to Z plus some punctuation. How the Caesar cipher works. XOR, I think this is operation. Instead of using XOR, like in the Vernam cipher, we use modular addition. Think of the numbers wrapping around a circle size 32 bits because 5 bits equals to 2 is to the power 5. If you add two numbers go past 31, you wrap around 0. Okay, let's let's say plain text equals to 26, which might be represent the letter this. Key equals to 21, then 27 plus 28 equals to 48. 48 more 32, which is 16. How does this mode works? And how does this 32? Okay, 32 comes from here, 2 is to power 5, I know. But how does this mode work? So the encrypted number is 16. This is what symbol means. Modular addition, modulo 32, real life analogy. Imagine a clock with 32 hours instead of 12. It's hour 27 and you move forward 21 hours. You land on hour 16. That's modular arithmetic in action. Exercise, can you find the key? Alice Bob changed the key. Alice sent a new encrypted message. You are given a cipher text and asked figure out the new key. How to solve? Guess the original message. Maybe it's the same in the previous example. Convert each character to 5 bit of number. Use the formula. C SAS C is the cipher text equals to plain text, and this is the Caesar modular. K, which is key, then we get key equals to Caesar's cipher text, and then we have this modular, and then we have this minus p, which is minus plain text, which means you subtract the plain text from cybertext mode 32 to find the key. The same key works for all pairs. Have you found one to try? If you want, I can help you write a simple Python script to convert letters to numbers, perform modular addition, try all keys, brute force to find one of the decrypt the message correctly. Hmm. I think I want to learn that modular, which is mode 32. How did you calculate? How do I calculate mode 32 for any text? Teach me mode. Excellent calculate mode and symbol. Modular arithmetic is like wrapping numbers around a circle. When we say a mod 32 means a reminder when you divide it by 32. What's the reminder when you divide by 32? Oh, so modular means divide, manual divide. Just divide the number by 32 and take the remainder. 48 more 32, which is 16. Like 48 divided by 32. 48 divided by 32 is 1. So the remainder is 16. Okay, so we'll put the reminder here as 16. I get this now. This is very simplest term now. I'm learning 75 mod 32, which is 11, and the divisible is 2, and the remainder is 11. I think it is 11 times. Okay. Remainder is 11. 32 into 2, which is 64, and if of minus 64 minus 75 minus 64, we have this 11, which is here. Okay, method 2, use Python. We have percentage, output 16, we have print this, and we have output 11. Well, this is easy real life analogy. 30 divided by 5 equals to 35. 35 more 32, which is 3. Easy. So you wrap up around the clock and land at hour 3. Why more 32 in cryptography? In Caesar cipher, for example, each character is represented by a number from 0 to 31 because bits 2 is to power 5 equals to 32 values. When encrypting, you add the key to the plain text number. If the result goes over 31, you wrap around using the mode 32. Caesar cipher, for example, let's say plain text 27, key 21. So we have the cipher text, this, and plain text plus key 27 plus, okay, then mod 32 is equals to 48 mod 32, which is 16. So, okay, if I minus 48 minus 32, then we have the 16. This is the reminder. We always put the reminder here. Would you like to try a few examples together to see? I think I like to write it down more than doing this thing. I hope so. But if some question comes like this, how can I do? Hmm. Let's ask Copilot if questions like above come in the examination, how do I solve this? Hmm. Provide previous example. I'm tomorrow. I cannot come. 10 Alice. Your task find the key. You then convert the message into numbers from the message. They converted into numbers. I think yeah. We have this MP plain text. We have this, and these numbers represent letters using 5-bit baud style, which is A equals to 0, B equals to 1, Z equals to 25, which is 26, 27, 28, 29, 30, 31. Uh, okay, we need to, you are given the cipher text in binary. Convert each 5-bit binary to decimal. Okay, we have to convert this into decimal. It converted into 4. How binary to decimal? Okay, they created all this, and we get the C decimal is this. Actually, I have this one too. The Caesar cipher uses C equals to PK mod 32 to find the key K equals to C minus P mod 32. Hmm. It is minus. Oh, okay. Actually, I should give this part too. Uh, think so. Sorry, I have a habit of copying it from my terminal, mostly Linux. 4. Okay, it created decimal, binary to decimal. Okay, binary to decimal, and then it comes here, and then it mm, minus from the plain text. and then do the mode 32, which is giving the reminder basically like minus. Okay, we have this algorithm running, and then final steps analyze the result. The key values are not consistent, they vary across the message. That means either the message is not encrypted with a single Caesar key or message is not the same. What to do? Convert the ciphertext binary to decimal, use known plain text if given, apply k equals to cp mode 32, check if the key constraint, if yes, that's your Caesar key. If no, the Caesar key is not simple as Caesar cipher. Python script, it's giving the Python script. Now we have the rot cipher, basic modular arithmetic. Okay, we will go there after once we learn this thing. The rot cipher or circular shift. Huh. In this cipher, instead of XOR or modular, we use the operation less than r. For example, less than r. Namely, bits shifted towards left in a circular way. Now, circular way, it's left in a circular way. C equals to encryption key, P is plain text is less than K, which is key, and then we have this ciphertext. Encryption cipher is the key used by Alice and Bob is an integer. Plain text equals to decryption key. We have the cipher, which is less than K minus K. Can you find the key K? K key. Explain the rod cipher. Uh, Rod cipher. Layman terms, how to solve the above question in layman terms. Explain me rod cipher in layman terms, how to solve the above question in layman terms with the real life example. Breakdown section, rod cipher, circular left shift. If your 5-bit binary like this, rotate it left by 3 positions. 3 positions. You are just moving bits left and wrapping the extra around. The right encryption and decryption. Encryption here will be like this. Rotate the plain text left by key positions. Decryption P uses this. Rotate cipher by 5 minus K positions. Okay. To undo the shift. And the key M equals to tomorrow cannot attend. Alice. Plain text here uses this. Yeah, we have the plain text, we have the ciphertext and decimal. How to solve it? Plain text number to 5-bit binary. Okay, here we are converting this to binary, which is 5-bit binary. 19 is 5-bit binary, 14 5-bit binary, 12 5-bit binary. Do this for all values. Steps. Try rotating each plain text by left k position for k equals to 1. Check which value of k constantly transforms each p into the corresponding c. When you find k that works for all or most values, that's your key. So we are finding the constant key, which is k. Shortcut key. Shortcut, try one pair. We have this P19 and 14. This is the first one, and We have converted this into 5-bit cipher. Try rotating left by 2. Okay. Yeah, this rotating this and how it is rotating to left. Hmm. K equals to key. We got the key. And in by clock with 5 dials, you rotate each dial 2 steps left to lock it, to unlock. To unlock it, you rotate each dial steps to right because 5 minus 2 equal to 3. That's how rod cipher works. I still not get it. Like, how do the rotation happen? Still not get it. Explain me how this rotation happens. For rod cipher, give me visual representation if possible. Hmm. Great. Let me explain now. 5-bit binary number. Okay. Okay. Rotate left means like this. Oh. Shift left. 1 and 2. Wrap around the first two bits. Final. Seeds, kids. 0, 1, 2, 3, 4. A, B, C, D, E. New seeds. 0, 1, 2, 3, 4. C, D, E, A, B. That's what rod cipher does to it. C, D. Oh, okay. So first two bits it takes to here. I see. So it must be like first two it's taking from here to there. Then 0, 1, 1. I think 0, 0, 1, 1, 1, 0. Yeah, yeah. Got it. Got it. Now I totally get it. And it's doing here is 3. So starting 3 parameters it's taking here and then it is fitting from the back end. Okay, I get it. Easy. Finally. Strategy, how to solve RAS cipher, convert P to C to 5-bit binary, try rotating P left 1, 2, 3, 4 bits, see which rotation gives you C. If the same K works for all characters, that's your key example from exercise. P equals to this, C equals to this. Okay, here we have just 1 and we are putting it here and yeah, done. And here we have 2, then we are taking these two and putting behind this. Get it? K equals to 2 works for the first pair. Try the next pair, which is like this. Okay. Okay, so the keys are 2 and we are putting it here and 1, 1, 0, 0, 1. Yeah, got it. So the key is 2. It works for all. Yeah, nice. I got it. I think this is going to be my first video. Modular arithmetic, basic modular arithmetic. It is a way to add, subtract and multiply and sometimes to divide, but not with integers but with reminders. Modular arithmetics deal with the study of the finite ring. Zn, z divided by n and z 0 comma 1, which is n minus 1, to get the remainder r belongs to Zn to the integer of the integer a belongs to z modulo n in Python r a percentage n Python syntax. Whose remaining is that? R equals to a mod n. And whose remaining is that? A equals to n multiplied by q plus r. N is modular, q is quotient, where r belongs to 0, comma 1, n minus 1, and q belongs to z. It is a way to add, subtract, and multiply, and sometimes to divide, but not with integer, but with reminder Python syntax. Okay, he gave me Python syntax. In this arithmetic, we may have all the basic operations like plus, minus, multiplication, divide. If we compute the module n, the result will be n m minus 1 because it's the reminder. Okay. If P is prime number, the ring ZP is also denoted by FP or GFP. Actually, GF means Galois field. A field is a ring but with four operations: plus, minus, multiplication, and divide. The notation means that, or in Python, A modulo n, A modulo, I think, A triple equals to B mod n. So here, this notation denotes that both the parts of the equation are modulus n. A modulus B mod n. A mod n equals to B mod n. A mod m equals to B mod n. Okay, so triple equals to is equals to mod. I told you. So A percentage n, B percentage n. These are the percentage. We take it as a modulo in Python and we are learning it. Great. It's easy. So, casting out 9 Prova del Nove, perhaps one of the earliest contacts with modular arithmetic is represented by so-called casting out nines. Check Prova del Nove Italian. Indeed, to check the correctness of a plain arithmetic operation, you mode 9 and check its validity mode 9, i.e. in the ring Zn, Z9 usually test is explained by using diagram which made it easy to understand, memorize to children. Here an example: somebody claimed that multiplication prova del nonne. This is a test to check that a multiplication has no mistakes when performed by hand. Okay, so this is a big multiplication. Without doing the multiplication, you can check it. Mode 9 is equal to 832 multiplied by this mode 9, which is mode 9, and so casting out 9s is 4 multiplied by 3 is 48, 48 equals to 3 mode 9. Now this is interesting. Here's the result: pass the check since 12 equals to 3 mode 9. Show that A modulo B and B modulo n if any of if n divides A minus B. The trick is to add the digits. So he multiplied it. Okay, got that. 8 plus 3 plus 2 equals to 13, which is equals to 4. Okay. 7 plus 1 plus 4 equals to 12, which is equals to 3. Yep, got this. 4 multiplied by 3, we have 4 3 are 4 9, 4 2 are 8, 4 3 are 12. So 1 plus 2 equals to 3. That's how he got 3. And yeah, so he added all the multiplication and he got the 3. So we are verifying the both of them equals to 3. So the test is right here. The modulus was 3. So no, the modulus was 9. So modular arithmetic with mode 9. This computation is fast way to compute the remainder of 832 divided by 9. This method uses so fast. So far, this is an example of arithmetic time complexity. Why this is true? Yeah, he multiplied it again, like 832, 8 plus 3 plus 2, which is 4 mod 9. I think he is doing that again here. It he's modding now. Okay. Iota. I think this is iota. Yeah. 8 plus 3 plus 2. Yeah, I told you earlier. So this is 13, which is 1 plus 3. 1 into 1, which is iota, equals 1 plus 3 equals to 4. Yeah, I know. Okay, 1 more 9. The rest of is 10 by 9. 10 by 9. Okay. It's easy. It's easy. He explained it easily. So, thanks to one of my friend, I'm able to get his notes, and he is very kind to me. So we covered almost casting out nines and modular 9, I think. The operation modular is an example of modular multiplication. Okay, so here we are having this arithmetic operation. For given 1 is to power 5, the operation has multiplication base 2 disregarding bits of position is greater than 5. For example, if 0, 1, 0, 1, 0, bit B, A equals to this, B equals to this, then we compute XOR A, XOR B by hand is this. We first put A, first put B, then 0, 1, 0, 1, 0, 1. I don't think this is right, but appears when we have the power of Z. If we have this case, the remainder is in binary. Modular addition in power of Z. These symbols are used also in checksums, SHA256 and SHA256. XOR operator, yeah, I know this one. Actually, if A be regarded integers and base, A equals to 10, B equals to 19, then 10, 19 equals to 30. Okay, now how this become like this? I need to solve Caesar cipher again. Hmm, got this modulo. In modulo, we have this reminder, I think. Yeah, so 10 divided by 19, 10 divided by 19. Okay, how does the remainder is coming? 30. Should be 9 or something like that. 10 on the 10, 19 on the 19. Still, because 10 multiplied by 19 is equal to 190. Okay, here it is multiplication. Ah, 10 multiplied by 19 is equal to 190 and 190 equals to 30 more 32. 190 equals to 30 more 32. More 32, we know that this is the Caesar cipher. Rod cipher is different. Caesar cipher is different in Python. Number of bits 32 equals to 2 is to power 5. Okay, 10 is to power 19. Percent 32 gives 30. Okay. Hmm. So that AB module. Find x such that equals to 1 and use brute force in week 6, and an efficient algorithm to do this will be explained. Okay, I am thinking that this will be my part 1. I am going to revise all the things that I have learned today in my copy so that I will not forget. We have covered Caesar cipher, we have covered Rod cipher, we have covered modular, Vernam cipher, Caesar cipher, Rod cipher. We have covered these 3 topics today, and yeah. So thank you for watching this video. This is my video 1, and we finished till page number 17, which is the operation of modular multiplication. Okay, sign out, peace. See you in the next video. Thanks for watching this video. Jai Shri Ram.